We are now ready for the limit comparison test, which is just another series test to prove convergence or divergence. The theorem goes like this. Let A sub n and B sub n be positive sequences, and then assume that the following limit exists. The limit as n approaches infinity of A sub n divided by B sub n, where L is finite and positive. That just means that when you take this limit here, you get a number that is greater than 0. If that happens, then the two series, A sub n and B sub n, either both converge or they both diverge. Here's an example, hopefully that will help clear up that theorem. We want to determine the convergence or divergence of this series right here. So we need to find ourselves another series, and we're going to call that one B sub n. And to do that, we are going to ignore all but the highest powers of n in the numerator and denominator. This is what we will use to compare our series with. So the highest power in the numerator will be the square root of n, and in the denominator it will be n squared. If we reduce this, we come up with this series right here. N equals 1 to infinity of 1 divided by n to the 3/2 power. This series that we came up with, n to the 3/2, converges by the p-series test. Remember, the p-series test states that if our exponent is greater than 1, then our series converges. So now we apply the limit comparison test, and we do that by taking the series we started with, a sub n, and we divide that by the series we came up with, which is b sub n. When we do this, we have to flip and multiply the denominator, which is what we get right here. Once we flip and multiply, then we reduce it, and when we do that, we will get n squared over n squared plus 1. Now the limit of this thing right here, if you use the n behavior, will get you a limit of 1. So since our limit turned out to be a number greater than 0, we can conclude that since the series that we found, this one right here, the b sub n, converges, that then our original series converges. So if the limit is greater than 1, since our series we came up with converges, the series we were given also converges. Okay, so let's look at another example. This one will prove divergence of a series. So we're going to start with this one right here. The summation of n equal 1 to infinity of n times 2 to the n all over 4n cubed plus 1. So we have to come up with a new series, the b sub n series. And to do that again, we are going to use only the highest term in the numerator and denominator. So that will be, there's only one term in the numerator, which is this one right here. And the denominator, the highest term, is 4n cubed. If we reduce that, we come up with this series right here, 2 to the n over 4n squared. This will be our b sub n, the series we are using to compare. Now that we have found the series that we're going to compare with, we need to determine whether this series right here converges or diverges. So we know that this diverges by the nth term test. If we take this right here and turn it into a sequence and see what happens as n approaches infinity, this sequence right here will approach infinity. And remember that if the sequence does not approach 0, then the series diverges. So the series that we have picked is that we are going to compare with is a divergent series. We now apply the limit comparison test. So we're going to take the limit of our sequence that we started with and divide it by the sequence that we just came up with. That will look like this. Our original divided by our new one that we found. Then we're going to flip and multiply, and then we reduce it, and this is what we come up with. 4n to the third over 4n to the third plus 1. And using n behavior, that limit will turn out to be 1. So by the limit comparison test, if the limit turns out to be greater than 0, then both series converge or diverge. Well, since the one that we picked, diverges, the limit comparison test tells us that our original one also diverges. Okay, here's one last example that I'll let you guys work on your own. It's the series n equal 1 to infinity of 2 to the n over 3 to the n minus 1. So as you work through this, we're going to compare it to 2 to the n over 3 to the n. Then we're going to flip and multiply them, and we are going to get a limit of 1. And so you will see that the series you compare it to is a geometric series with a radius of 2/3. So that geometric series will converge. So when you compare it to this one and you go through the process, you flip and multiply and you find your limit to equal 1, you will be able to conclude that this series right here converges because the series you compared it to converged and their limit was equal to 1.